Welcome to UGC lecture series Linear Integrated Circuits. In this lecture we are going to see about the Wien-Bridge oscillator, its derivation of frequency of oscillation and design of Wien-Bridge oscillator. So, this is a Wien-Bridge oscillator circuit. Here it is in the shape of Wien-Bridge. So, we know that in the bridge circuit there are 4 arms. Here also if you look at the circuit, there are 4 arms. In one arm the resistor and capacitor are in series, and in another arm the resistor and capacitor in parallel. The other 2 arms have the resistors RF and RS. So, this circuit diagram is considered as a bridge circuit, and it is like a Wien-Bridge circuit. So, it is called as Wien-Bridge oscillator. And when you look at the circuit, the signal is given to the positive terminal here, and so the amplifier is not going to produce 180 degree phase shift. So, the feedback network is actually there is no phase shift in the feedback network also. So, since the amplifier is now a non-inverting amplifier. In the case of RC phase shift oscillator, the amplifier itself produces 180 degree phase shift and the feedback network produces another 180 degree phase shift. So, the phase shift, the entire phase shift is 0 degree. Now, this amplifier is a non-inverting amplifier, so 0 phase shift produced at the non-inverting amplifier. So, no feedback at the no phase shift at the feedback network. Again we have to derive the frequency of oscillation for this Wien-Bridge oscillator also. Consider this as this parallel combination as Z2, this series combination as Z1, and beta is actually Z2 by Z1 plus Z2. So, what we have calculated previously in the RC phase shift oscillator, we have calculated what is beta value, and from there we have calculated the value of A. From the Barkhausen criteria, magnitude of A beta must be greater than or equal to 1. Same way we have to calculate what is beta here, and from beta you have to calculate what is A and the frequency of oscillation from the beta value, from the beta equation. So, what is Z2? It is the parallel combination of R and C. So, consider these R and C as this R and C as R2 C2 here, this R1 C1 in the in series combination as of now. So, finally, we will make all these resistors and these R1 and R2 are equal and C1 and C2 are equal. Before deriving, you consider these 2 resistors are not equal, capacitors also are not equal, and Z2 now will be R2 into 1 by C2S divided by R2 plus 1 by C2S. If you take LCM, it is R2 C2S plus 1 by C2S. So, these 2 terms will get cancelled. Finally, it is R2 by 1 plus R2 C2S. What is Z1? It is the series combination of R1 C1. So, you will have R1 plus 1 by CS. So, if you take LCM, R1 C1S plus 1 by C1S. This is Z1. For beta, if you substitute the values of Z2 and Z1, beta is Z2 by Z1 plus Z2, substitute the values of Z1 and Z2. If you simplify this, you will have R2 by 1 plus R2 C2S divided by, take LCM, R2 into 1 plus R1 C1S plus R1 into 1 plus R2 C2S divided by 1 plus R2 C2S into 1 plus R1 C1S. So, these 2 terms will get cancelled and you have finally R2, this term will be in the numerator of beta. So, R2 into 1 plus R1 C1 S divided by R2 into 1 plus R1 C1 S plus R1 into 1 plus R2 C2 S. This is now beta. Now you simplify again. If you multiply all the terms R2 inside and R1 inside here, you have beta is equal to R2 plus R1 C1 S R2, R2 into R1 C1 S divided by again R2 plus R2 R1 C1 S plus R1 plus R1 C1 R1 R2 C2 S, R1 R2 R1 plus R1 R2 C2 S, C2 S. So beta will be Z2 by Z1 plus Z2. So Z2 we have calculated it as R2 by 1 plus R2 C2 S divided by Z1 is R1 C1 S plus 1 divided by C1 S plus again Z2 is R2 by 1 plus R2 C2 S. So now simplify and take LCM. Numerator you keep as such R2 by 1 plus R2 C2 S. In the denominator this term you keep as such. In the denominator if you take LCM, then it is 1 plus R2 C2 S into 1 plus R1 C1 S plus R2 C1 S divided by C1 S into 1 plus R2 C2 S. So these two terms will get cancelled. This, if you take this R1 C1 S in the numerator, you have beta is equal to R2 C1 S R2 C1 S divided by 1 plus R2 C2 S into 1 plus R1 C1 S plus R2 C1 S. You multiply this R2 C1 S divided by, if you multiply you will get 1 plus R2 C2 S plus R1 C1 S plus R2 C2 S R1 C1 S divided by R2 C1 S. So if you multiply this 1, you will get 1 into R1 C1 S, you will get it R2 C2 S, right. So now you take the common terms. If you have S, then take S out, and if you have S squared, you take S squared out. So 1 plus, you have S term here, and another S term here. So take S out. So you will be getting R2 C2 plus R1 C1 plus R2 C1 plus you have one S square term. So S square into R1 C1 R2 C2, and we know that S is equal to j omega, S square is equal to minus omega square. If you substitute this value, you have S is equal to j omega R2 C1 divided by 1 plus, again S is equal to j omega, the entire term R2 C2 plus R1 C1 plus R2 C1 minus omega square into R1 C1 R2 C2. So, this is now your beta. See there, the numerator also have a j term. So, now we want to make this beta to be real. If beta to be real, what you have to do is consider this j omega term. So, you keep the j omega term in the denominator also. So, only the real part can be equated to 0 now. So, it is 1 minus, what is the real part? It is 1 minus this term omega square into R1 C1 R2 C2 is equal to 0. Omega square R1 C1 R2 C2 is equal to 1. Omega square is actually 2 pi f square is equal to 1 by R1 C1 R2 C2. F is equal to, f square is equal to 1 by 2 pi square R1 C1 R2 C2. If now you equate the resistors and the capacitors, if you put the equal resistors and the capacitors, then you have F is equal to 1 by 2 pi R C. This is an important formula for the frequency of oscillation of Wien-Bridge oscillator. And now we have to calculate the gain, for which the beta, the remaining part of beta is, actually we have equated the real term of beta equal to 0, since the denominator and the numerator must have j part to cancel out for the beta term to be real. So, in the numerator you have j omega R2 C1, j omega R2 C1 divided by, in the denominator it is j omega R1 C1 plus R2 C2 plus R2 C1. This is in the denominator. Now, if you cancel out this j omega, then beta is real, and we have already assumed the resistors are all equal and the capacitors are all equal. So, beta is equal to, if you make this R2 as R1 C1 divided by R1 C1 plus R1 C1 plus R1 C1. So, you will have R1 C1 as common in the denominator. You have only 1 by 3. This is your beta, and the Barhazen criteria says that the magnitude of A beta must be greater than or equal to 1. So, A must be greater than or equal to 3 here. Since beta is 1 by 3, if you want to make this greater than or equal to 1, this product, then A must be greater than or equal to 3. And see the circuit of the Wien-Bridge oscillator. It is the signal given to the positive terminal, and so it is the non-inverting amplifier. If it is a non-inverting amplifier, what is the gain of the non-inverting amplifier? The gain is actually 1 plus RF by RS here. It is RS. So, A is equal to, which is equal to 1 plus RF by RS, and from this RF must be greater than or equal to 3 times Rs. This is the gain of the non-inverting amplifier. From here you are calculating Rf greater than or equal to 3 times, not 3 times, you have 1 here. So, 3 minus 1 is 2. So, 2 Rs. So, this is the value of the feedback resistor. So, we have calculated the gain of the non-inverting amplifier as 1 plus Rf by Rs, from which Rf is greater than or equal to 2 times Rs, the input resistance, Rf is the feedback resistance. And also we have calculated we have derived the frequency of oscillation as f is equal to 1 by 2 pi Rc. So, for designing the Wien-Bridge oscillator, these two values or formulas must be very important. So, the design, if the design is design a Wien-Bridge oscillator to oscillate at 100 hertz, then frequency of oscillation is given, f is given, and we know the formula of f is 1 by 2 pi Rc, which is given as 100 hertz, and assume the value of capacitor as 0.1 microfarad. It is 0.1 microfarad, C as 0.1 microfarad, and the value is substituted in the frequency of oscillation and find out what is R. R is calculated, and what are the passive components present in the Wien-Bridge oscillator? If R is calculated, then these two values R1 and R2 will be taken as the value of R, and we have assumed C1 and C2 as 0.1 microfarad. So, the series arm and the parallel arm of the Wien-Bridge is calculated now. The remaining two resistors are this Rf and Rs. This Rf and Rs is calculated from the gain of the non-inverting amplifier. So, AF is 1 plus Rf by Rs, which is actually, we have calculated it as greater, Rf is greater than or equal to 2 times Rs. So, now you assume this Rs as 10 kilo ohms. Normally the input resistors for any amplifier is assumed as 10 kilo ohms, and so what is the value of Rf? From this equation you can calculate the value of Rf as 2 into 10 kilo ohms. So, it is 20 kilo ohms. So, this is the design of the Wien-Bridge oscillator. So, in this lecture we have seen Wien-Bridge oscillator. In the Wien-Bridge oscillator there are 4 arms in the circuit, as in the case of Wien-Bridge, where in one arm we have two passive components which are R and C connected in series, and in second arm there are parallel combination of R and C, and the third and fourth arm has the resistors Rf and Rs. Since it is having the bridge shape, it is called, and as Wien-Bridge shape, it is called as a Wien-Bridge oscillator. This bridge, when the bridge is balanced, then the phase shift is considered as 0. So, initially the bridge is getting balanced and the phase shift is 0, and the noise present in the input of the amplifier will be taken as the input of the oscillator, and it is getting amplified only when the phase shift is 0. So, this is one of the Barkhausen criteria such that the oscillator oscillates to when the oscillator meets the Barkhausen criteria, then only the oscillator will generate the output as a sine waveform. So, we have discussed the basic of oscillator as we have a amplifier in the input side and we have a feedback network. So, the amplifier takes the noise as the input signal initially, and it gets amplified by the amplifier and produces the output as the product of the gain of the amplifier and the input, and this is fed back to the feedback network, which has the gain as beta, which is producing the output as the feedback voltage Vf, which is nothing but the product of A beta into Vi. So, A beta, if it is equal to 1, the product of A beta is equal to 1, then the feedback voltage is equal to exactly identically equal to the input voltage. So, now what we have to do is, when the product of A beta is made as 1 and also the other condition on phase is A beta, the phase shift in the loop gain must be equal to 0. If both these conditions are satisfied, then the oscillator will generate an output and the sustained oscillation will be the output because of the non-linearity property of the transistor. So, this initially the noise voltage is the input for an oscillator. There is no external signal given for an oscillator, only the noise is taken as the input and which is getting amplified and fed back to the input of the amplifier again and again. So, since the amplifier is working in the non-linear region and the output will be a sustained oscillation, even the amplifier is amplifying the input, the output is not going to amplified increasingly. It gets sustained once the transistor will go to the saturation mode. This is the basic of the oscillator, and normally the difference between the amplifier and the oscillator is, for the amplifier we will be giving an input signal externally, and for the oscillator there is no input signal. Without an input signal, oscillator produces the output. And the other important difference is, the amplifier has the negative feedback and the oscillator has the positive feedback. These are the two major differences between the oscillator and the amplifier. So, the amplifier has the input signal externally, and in this IC 741 we have two configurations of amplifier. One is the inverting amplifier, the next one is the non-inverting amplifier. So, in any of the amplifiers can be used as an amplifier in the oscillator circuit. If an inverting amplifier is used, then to satisfy the Borkhausen criteria, we have to produce a 180 degree phase shift, another 180 degree phase shift to maintain the phase condition. What is the phase condition is A beta, the phase shift in the loop gain must be 0 or multiple of 2 pi. So, if the inverting amplifier produces 180 degree phase shift, then the feedback network should produce another 180 degree phase shift. So, this concept we have seen in the RC phase shift oscillator. In the RC phase shift oscillator, there are 3 RC stages which produces 180 degree phase shift in the feedback network, and the inverting amplifier produces another 180 degree phase shift. So, the total phase shift is now 360 degree. So, which is one of the condition of the Borkhausen criteria. Oscillator must satisfy the two conditions of Borkhausen criteria simultaneously to generate the output signal. And in the Wien-Bridge oscillator, we have seen that the amplifier is a non-inverting amplifier. So, there is no phase shift between the input and the output voltage, and so the feedback network need not to produce other 180 degree phase shift as in the case of RC phase shift oscillator. So, the Wien-Bridge oscillator, the phase shift in the loop gain of the Wien-Bridge oscillator is 0 once the Wien-Bridge is balanced. So, once it is balanced, then we consider that the phase shift in the loop gain is 0 degree. So, the oscillator produces a sustained oscillation in the Wien-Bridge oscillator, and we have derived the frequency of oscillation in RC phase shift as well as the Wien-Bridge oscillator, where you have to remember the frequency of oscillation of RC phase shift oscillator has 1 by 2 pi RC, 1 by 2 pi RC root 6, But in the case of the Wien-Bridge oscillator, it is only 1 by 2 pi RC, there is no root 6. Only root 6 makes the difference between the frequency of oscillation of RC phase shift oscillator and the Wien-Bridge oscillator. And what is the value of A? The A is the amplification factor of the amplifier. What is the value of A in RC phase shift oscillator is, it is greater than or equal to 29, and since it is the inverting amplifier, it is minus RF by RI, which must be greater than or equal to 29. So, RF must be greater than or equal to 29. That is the case in the RC phase shift oscillator. In Wien-Bridge oscillator, the magnitude, that is the amplification factor of the amplifier is, it is 3. So, here it is a non-inverting amplifier. So, 1 plus RF by RS must be greater than or equal to 3, and RF must be greater than or equal to 2 from the formula. So, these are the two formulas you have to remember while designing the oscillators. And one more important point is, in RC phase shift oscillator, the input resistance which is given to the non-inverting terminal of the RC amplifier must be 10 times of the resistor present in the feedback network. So, these are the points you have to remember for designing the oscillator, either is a RC phase shift oscillator or a Wien-Bridge oscillator. And we have designed an oscillator for the frequency of oscillation as 100 Hertz for both the oscillators. These are the reference. Thank you.